Yeah. Okay, so last day, what we discussed is basically, what did we discuss? Yeah, so we talked about qubits and multiple qubits, right? Yeah, and before that we talked about classical gates. Okay, classical logic gate. So what is a logic gate? If I just recall, what is a logic gate? Okay, so before defining logic gate, we talked about problems like functions. Okay, that which you need to compute. So for us, problem is, let's say, a function where there is some input. Okay, let's say this, and to let's say some 0, 1 to the power d. Okay, for example, if let's say n equal to 3 and d equal to 2. Okay, so we have possible inputs which are 0, 0, 0. Okay, and 0, 1, 0, and so on. Okay, so there will be 8 possible inputs. So we can always say here that we have one or more bits, okay, as input. So here I can say 1, 1, 1. So these are possible input, and for each input we'll have a corresponding output. So yeah, so this is an element of, let's say, d equal to 2. I can assume that, let's say, this is 0, 1. Okay, this is 1, 0, something like that. So each of these will be something. Let's say 0, 1. Doesn't matter. So this is such a function. Okay, such a function. And then we said, okay, what is a logic gate? Logic gate is kind of a physical device that takes these as inputs. So inputs is like one or more bits, or you can say Boolean variables, okay, Boolean values, okay. So 1 is interpreted as true, 0 is interpreted as false, and of course it will produce this kind of depending on the value of d, it will produce this kind of tuples. But when it produces this kind of tuple, so basically f can be said as like, okay, f is going to give some f1, f2, fd. Okay, we can divide this as individual functions. Okay, and then if you want to compute what is fx, so they are all individual functions, f1, f2, fdx. So it's less like math 1. So for fx, we have this function f1. I mean, if you just say for some x, input x, f1 will have some output, f2 will have some output, and so on. So given any kind of a function like that, okay, kind of Boolean function like that, we can always say that it can be decomposed into functions like f1, f2, ft. So ultimately, each of this can be considered. Okay. So and in basically the classical computation, okay, entirely depends on that. So if you want to compute this kind of a function, so you have to so you have to compute this individual functions f1, f2, and dot 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 fd. And then we talked about, because I'm going to talk about conjugates, so just I'm recalling what we said, and I think I missed one point. So that is something called irreversible and reversible gates. Okay, so for example, when you talked about, let's say, AND gate, let's say A and B, where A, B could be 0 or 1. So we had a truth table, let's say A, B, and then we have A not A and B here, for example. Let's say if it's 0, 0, then it will be 0, 0, 1, it will be 0, and 1, 0, it will be 0, and 1, 1, it is 1. So at this gate, okay, I can always say this is irreversible. Irreversible means irreversible. Irreversible means from the output, we cannot determine uniquely what is the input. So we can have only possible inputs. For example, 0 is the output here, but it can have multiple inputs corresponding to which 0 can be produced. Okay. So similarly, if you take A, or B, then that is also an irreversible gate. Okay. So those gates are not reversible. Okay. Yeah, so when you talked about quantum, okay, like quantum evolution in the postulate 2, I think, okay, or maybe postulate 1 in quantum mechanics, then we said, okay, this is always a unitary evolution. So if we have a new state, Okay, whatever the gate, whatever it is, okay, if you give some input and if it produces an output, let's say, so this is like some x, okay, this could be in some space which is a tensor product of some vector. So if it is, let's say, an n qubit, so then this is here, so dot 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 up to c square, okay, n times, okay, then that is n qubit, and it produces, let's say, a d qubit, or which is called also a qubit. So it is, let's say, n qubit, okay, and it can produce, let's say, I can just say q date, it is d-dimensional. So let's say this is y, or you can say this is u. If this is this u has to be unitary, so it is just like u times x. Okay, and this you then like if it is a qubit, like d-dimensional, so you have to multiply. So this is d qubit, means it is equivalent. It is saying you have d qubits. Okay, this is just a name people use. Okay, qubit means just d qubits. Okay, so then it will be like c square. So this is the qubit space. Okay, and the tensor product c square. So this is d times. Okay, here. So qubit here it is like, okay, n times. Okay, and of course, then if you want to realize this, okay, the dimension of x, if you consider, so this is c to the power 2 to the power n, okay, and then so u has to be a unitary matrix, so it has to belong to c to the power n times 2 to the power n, and of course u is unitary. So now what is happening here is, so for example, like if you consider and OR gate, okay, classical OR gates, they are not reversible. Reversible means for every unit, I mean, you cannot get back to your input from the output, okay, uniquely. That's the problem. But here we can always say it is always possible. I mean, due to the postulate of quantum mechanics, it is always possible. So if you just get y from x, so which is ux, so if you just operate u on this, and then again you operate u star, okay, u star, or sometimes people write u dagger, doesn't matter, the same meaning. If physics people used to write u dagger, and maths or computer science people used to write u star, but it doesn't matter. Okay, how do you denote it? But if you apply that again, you'll get back x here again. So this is the output here. Let's say y. Okay, this, or let's say y. So you can get input to output, and again you can get back your input, and this makes a lot of difference. Okay, I'll talk about that. But the question here is, can we have classical gates as well, which are, let's say, reversible? Okay, and then another question. Okay, so here is a question: can you have classical gates? Because if this is only the power of quantum computing, then this possibly also can be achieved using classical gates. Okay, so then the question will be, okay, which gates are reversible classical gates? And then the question will be, are they universal? Universal, as we defined before, a gate is universal if like any kind of, I mean, this is a sufficient gate, I would say, where if you want to compute something, okay, so your desired computation can be computed, okay, just by that single gate. Okay, so that gate is universal. So the question here will be, does there exist any reversible gate, okay, which is universal in classical computation? Okay, so does there exist a reversible gate which is universal? So that's the bigger question. And then the question will be, why, if it is universal and if it is reversible, why don't people implement that? Okay, so
Sir,
that's a separate
excuse
question.
me, sir. In the previous example, x is a qubit and ux is a qubit, is it?
This is the n qubit.
Yeah,
So
n
x is,
qubit and y is an d qubit. That means how can you be?
sorry. So it also has to, so I was talking about class. So see, it shows you. I think I did a mistake here. It always has to be this n times. Otherwise, we do not have this unitary. Yes, you're correct. You're correct.
Okay.
Yeah, sure. Yeah, I did a mistake. So the question is, does there exist a reversible gate which is universal? Okay, that's the question. And the answer is yes. Okay, there are gates which are universal, meaning I mean, there are gates which are reversible as well as universal. Okay. Okay. One example of very simple reversible gate is a NOT gate. Okay. What is a NOT gate? It takes 0 to 1. Okay. And so this is a classical gate, then 1 to 0. Okay. So yeah. So this is a reversible gate. And when we talked about universal gates, so we gave some examples also, which are like universal gates. For example, NAND gate is a universal gate. NOT gate is also universal. And I think other gates, there are other gates also which are universal. I mean, we'll talk about it maybe today a little bit. So yeah, so for example, NAND gate, okay, and NOT gate, these are all universal gates. And AND gate, okay, these are all universal gate. I mean, how do you prove that? So once you prove that one gate is universal, then if you want to prove that the other gate, another gate is universal, you just have to write the universal gate, let's say this one, in terms of the other gate. Okay, then we can prove. So if this is known that this is universal, okay, then how to prove that this gate is universal, let's say. So you have to compute this. Okay, you have to compute this NOT gate, this universal gate, using only this gate, like the NAND gate. Okay, then you can show that this is universal. Okay, this is how it is shown in literature, but I'll not go into that. I mean, this is very simple. Okay, this is very simple. Any book, I mean, you will get it. So there are many reversible gates, but the question is whether in the classical computation, okay, whether they are universal or not. That is the question. They are all universal gates, but in the world of reversible gate, okay, whether they are universal or not, that's a bigger question. Okay.
Sir, when you say a reversible gate, is it like a set of gates which can sorry, when you say universal gate, is it like a set of gates which can realize any gate, or is it
No,
just
no,
like
no. Like one single gate. So I guess
okay? So
okay, one
how is
simple.
so not is not universal gate, is it?
I think not is universal.
It won't realize and or anything else, right?
Not now. I mean, there may be a way to do that. I think there is a way to do that. For example, NAND. I mean, if you want to write NAND, for example, okay, NAND gate is universal.
NAND is
So
universal, yes, sir,
yeah, yeah.
but not and
NAND you can write. NAND you can write in terms of, I think. I mean, suppose you want to write. Okay, so maybe we can do this. So yeah. So let's say, suppose I want to realize NOT gate. Okay, so then the
no, sir.
question.
Realizing NOT gate is from NAND gate is fine, sir. I get it. NAND is universal,
Okay,
but
yeah,
not
yeah.
can't be universal because using NOT gate we can't realize other gates.
I don't remember exactly, but let me remember. Boolean function not get. I don't remember it. So maybe what did I say? I mean, I forgot. So anyway, so if it is not, then it is okay. Okay, but the thing is, if I can show that one gate is universal, then other gates, okay, like using other gates, okay, if that can be implemented, then we can say that the other one is also universal. Okay, for example, here, if I can implement a NAND using NOT, okay, since I know, let's say this is universal. Okay, in that case, I can use if I can implement this NAND gate using just NOT gate, then I can also say that NOT gate is universal. So that's the logic. Okay. So
Yeah,
now,
but
Sir,
that
but
only if we can do it, right?
yeah, if we can, yeah, if we can.
sir, but NOT gate is a single bit gate and NAND is 2-bit gate. So you need at least one more 2-bit gate to prove not NAND in terms of not, right?
NOT is from one like from Hamming space one
The,
to Hamming space one.
yeah, NOT is NAND is not one. Yeah, not and yeah. Yeah, so the thing is, okay, I'll come to that little bit later maybe. So because I'll be talking about reversible gates, okay? I mean, how this number of bits is playing a role here, okay? So I'll do that. So, but okay, so what is the advantage of having a reversible gate, let's say, or irreversible gate? So for irreversible gate, we have to erase some information, and which we talked about, like, okay, if you erase some information, there will be a dissipation, okay? There will be energy which will be dissipated. And so that's why, okay, so because of that energy, there could be, I mean, so you are losing some energy, you can say, or in some sort of other way of saying it, like you can generate some heat, okay, in your microprocessor and so on. Now Yeah, NOT gate is one example of a reversible gate. So question is whether it is universal reverse gate or not. That's the question. And you can have other reversible gate, for example, swap gate. Okay, swap gate. So what was that? So swap gate like AB will go to BA, right? So this is also reversible. Okay, this gate is also reversible. So this is an example of a reversible gate. And there is another gate, okay, which I think I did not talk about, which will play the quantum analog of that gate will play a very big role in quantum computing. We'll talk about that. And I think that will be that is called control not gate. So that is called C not gate. Okay, C not gate, and sometimes C not gate. Okay, so this is swap gate. C not gate. What is it? So sometimes okay, so it is denoted. I mean the icon which the people used to do it is like this. Yeah, so this is like some, let's say A dot B. If A and B the outcome, let's say A and B, and then they used to write it like this. So yeah, so this is A. Okay, so control not. So this is control not. Okay, control not gate. So what does it do is, so if you want to just write down the truth table, so it is like, okay, so if we have A and B, okay, and let's say I write this is the C naught gate, the output. Okay, so if it is 0 0, it will give you 0 0. I'll tell you why it is called control, how it is controlled. And so 0 1, then it is 0 1, and then 1 0, it will go to 1 1, and then 1 1, so this will go to 1 0. So what is happening if you observe carefully this table? Okay, when there is this first, okay, a bit is 1, then the corresponding second bit is flipped. Okay, otherwise it is remain invariant. For example, the first two, there is no change here. 0 0 will produce 0 0. 0 1 will produce 0 1. Okay, 1 0, see the second bit is flipped here. Okay, this is 1 from 0, and when it is 1, again the second bit is flipped. So when you are giving the input, let's say A and B, so there is one gate which is controlled, in other words the target. So second bit here is the target, and first one is controlling that. That means the operation, okay, when we are producing the output, okay, and giving the input, so if the first bit is 1, then only it will flip the second bit. Okay, so the target is controlled. So it is, this entire operation is controlled by this, and this is control not, because flipping means actually not. Okay, you are applying the not gate. So yeah, so that's why it is also called control not gate. Okay, this is again, now you can see that this is a reversible gate. Okay, from the output you can say what is the input, because you have 4 different outputs for 4 different inputs. So this is an example also of a reversible gate. Okay, this is also example of a reversible gate. But again, the question will be, is it a universal gate, okay, or not? And yeah, and there are other gates, but those gates will need more number of bits. For example, there is something called Toffoli gate. I think TOFFOLI. Toffoli gate. Okay. And so this is a peculiar gate where you need actually 3 bits as input. Okay. And it goes as follows. Okay. So if we just write down the truth table, so it will be, let's say, A, B, C, these are the input, and A dash, B dash, C dash. So let's say these are the corresponding outputs. Okay, so 3-bit input, 3-bit output. So it is 0, 0, 0 will produce 0, 0, 0, 0, 0, 1 will be 0, 0, 1. Okay, and just look at the pattern and tell me whether we can also say this as controlled something, okay, or not. Like previous C naught gate was control not. Can you say this as control of something or not? So 0 1 1 0 1 1 1 0 0. So this will be 1 0 0, and 1 0 1. This will be 1 0 1, and then 1 1 0. This will be 1 1 1. 1 1 1 will give you 1 1 0. So any idea? Can it be explained as control of something, or something like that?
Uh, First two are controlled and last one is the target. CC not like.
Yeah, it is a control not. So you can say this is controlled. So controlled Okay, control C not gate. C not gate. Okay, or otherwise you can say control not gate. Okay, so if there are two ones here, then only the third bit is getting flipped. So that means otherwise everything is same. The output is same. So it's a control not gate. Okay, so it's a Toffoli gate, and you can see here again. So this is also a reversible gate. Okay, this is also reversible. This is also a reversible gate. And another example of a reversible gate is something called Fretkin gate. Uh, Fretkin gate. Okay, so this the output and input is like that: A, B, C, A dash, B dash, C dash. Let's say, and if you have 0, 0, 0, then you have 0, 0, 0, 0, 0, 1 will go to 0, 0, 1, 0, 1, 0. You can observe that whether this can be explained as control or something or not. 0, 1, 1 will give you 0, 1, 1. 1, 0, 0, let's say, then it will give you 1, 0, 0. And then 1, 0, 1 will give you 1, 1, 0. And again, 1, 1, 0, 1, 0, 1, and 1, 1, 1. 1, 1, 1, it will give you, 1, 1, 1 will give you 1, 1, 1. Any idea what kind of gate it is? This is
The first one is control not of the first. I mean, the second one is control not of a, and the third one is again control not of a.
this is actually control. Yeah, so this is actually control swap gate. Okay, so where does it change? From here it is started changing, right? So if this is 1, then only there will be swap between these two. Okay, if this is 1, then say 0, 1 is changed to 1, 0. If this is 1, then 1, 0 is changed to 0, 1. Okay, if it is 1, then of course 1, 1 is changed to 1, 1. So this is what is called the control swap gate. Okay, and in fact, okay, I'm not going to prove it, but in fact, the gates, the smallest gates, okay, which are reversible in classical computation, which are reversible and universal, okay, they are nothing but this Toffoli gate and the Fretkin gate. So Fretkin gate and the Toffoli gate. So Toffoli and Fretkin, okay, both are universal, reversible, and universal. Okay, so of course, then the question will be, why don't you use that? Okay, in the classical computation. Okay, then there will not be any dissipation of energy, except the fact that, okay, so if you want to give them some input, they will produce some output. Okay, copy the output and again get back to input doing just the reverse operation. Okay, because it can be obtained. So from output, you can obtain the input. You get back to the input again and use for another purpose. So only dissipation of energy could happen only when you are copying the output. Okay, this is the only chance of, let's say, energy. So then the question will be why the computational world, classical computational world, should not use this Fretkin and Toffoli. By the way, the question you were saying, like, for example, here you need at least 3 bits to perform this Toffoli gate, and you need 3 bits at least to compute this Fretkin gate, because these are the smallest. Okay, so these are the smallest in terms of input. Okay, so smallest. Okay, so yeah, so they are the smallest gates. Okay, which are both reversible and universal. Then why not the classical computation would do that? So basically, what I meant by that, when you are designing your system, okay, or if you are creating your microprocessor, or where you are using all these gates, okay, because any operation now can be implemented in terms of using this Toffoli and Fretkin. So why not do that? And people are trying to do that, but there are some technical disadvantages, okay, which I'm not going to talk about. But if you're interested, you can read some books. So where you will find there are some technical disadvantages. Theoretically, everything is fine. There is no problem. Okay, but technically there is a problem. And the next question would be, okay, what I wanted to ask here. So, so these are US. I mean, sometimes I forget what I wanted to say. Yeah, I think. Yeah. So, yeah. So since this is a 3 minimum number of bits you require is 3, so we have to use. Okay, there's something called ancillary bits for performing this operation. Okay, we have to add some extra bits, okay, in order to perform this kind of operation. Okay, so if you want to do a reversible computation using a classical computer or in a classical system, let's say, we have to use some ancillary. Okay, otherwise it's not fun. So this is the answer. That's what you asked. So ancillary, I think this is the spelling, double L E, ancillary bits. So you have to use some ancillary bits. So I'm not going into details of that. Okay, we'll do it in quantum. We'll see a lot of algorithms where people will use some ancillary qubits, but so here you can at least see, like, for example, if this is universal, like the Fretkin gate, so you need 3 bits at least. So suppose you want to realize the NOT gate, okay, so that means you need some ad hoc gate. So suppose for 0 I want to produce 1, okay, this is the operation. Okay, I want to use Fredkin gate or Toffoli gate. So that means I need to add some extra bits here, which are additional. Okay, then only I can somehow use this, let's say this Fredkin gate or a Toffoli gate. And these two, the job of these two is nothing, just to implement something so that finally whatever I get, I'll only measure this one. Okay, and this one I'll just forget whatever it produces, 0 or 1, I don't care. But here when you get this 0 goes to, then I'll say it takes 0 to 1, okay, or 1 to 0, then it will, or yeah, so then it will realize NOT gate. Or maybe if you want to use NAND gate, okay, the same thing will happen. So you have to there at least one extra bit, so which is the ancilla bit. Okay, yeah, and another important thing is there is a role of permutation matrices here. I mean, what is happening is, since this is classical, okay, let's say, so this is, let's say, f from Cn, let's say 0, 1 to the power n to 0, 1 to the power n, because now it is not a problem to consider this n here as well, because we can extra add, even if it is less than, let's say, d is less than d is less than n, then we can add some extra ancilla bits, which I'll not measure. I mean, the values of that is not important, okay, in the output. But I'll only measure what is the required, let's say, okay, or those bits, or d many bits, let's say. What are the values of that? That is enough to implement this function. So I can always assume that those are ad hoc, okay, ad hoc bits I added. So now f of 0, 1 to the power n to 0, 1 to the power n. So what if it is universal? Okay, so there must be somehow, okay, some unitary matrix probably can play a role here, okay, because what is happening is, so there are n bits, okay, so 0 to the 1 to the power, okay, there is another dimension to this, which, okay, I'll skip, but just to give you the dimension is, so this is also a vector space, by the way, okay, over the finite field 0, 1, okay, so this is also a vector space, and there are 2 to the power n number of vectors, so that means there are 2 to the power n number of possible inputs for this kind of a function, okay, and here also there are 2 to the power n number of possible bits, okay. So somehow, since this is like reversible, then you can suppose it is reversible. I have to implement the reversible computation, okay, and then of course if I have a gate, let's say, for example, which is a reversible gate, okay, and I can have a combination of those gates as well. But let us assume that suppose I have just a reversible gate like Fretkin gate or let's say the Toffoli gate, there must be some connection with some matrix, okay, because the dimension, because it is a function from a vector space to a vector space, okay. So, and here each input can be like I can interpret them as vectors. So let's say dot dot dot. So there are n entries. Okay, so all entries are in 0, 1. So I can just say okay, yeah. So it is, yeah. So it is in 0, 1 to the power n. So it, yeah, of course this is dimension n cross 1. Okay, I can of course say that. And this, since this is a vector space, now there is a sense that, okay, probably there must exist some unitary, okay, which will realize that. But since I'm computing in a finite field, okay, my field is my field is, if you know this, okay, just to relate to your math 2 course, okay, the field here is actually 0 and 1. This is called a Boolean algebra, by the way. There was a mathematician called George Boole. So this is Boole. So Boolean algebra. So here, okay, so what you do is the matrix would be also on that particular field, because when you consider in math 2 a matrix from a vector space to a vector space, let's say let me define T from a vector space B to another vector space and say, let's say this is a vector space about the field R, this is a vector space about the field R, then you always have a realization, okay, which is a matrix, which is a real matrix. It depends on the field. Now, since here we have a similar kind of a situation, okay, vector space to vector space, and the field is 0, 1. So I'm expecting a matrix, okay, so whose entries are only 0 and 1. So, and I want this to be like an orthogonal matrix, like a unitary matrix. So my first observation and my first hint or intuition should be on permutation matrix. And the question is, so this is a question which I'll not discuss. Maybe I'll give it as a homework. So which is, can I realize all this reversible gates using permutation matrices? Okay, and the answer is yes. So here is a question which is like understanding. Just a minute. So understanding the reversible gates in terms of permutations or permutation matrices, because permutation matrix is unitary and it contains only zeros and one permutation matrices. Okay, in fact, in a permutation matrix, what we have is there is only one non-zero element in each row and each column. Okay, there is only one element which is non-zero, and that element is 1, and all others are 0, because it also has to be orthogonal. Okay, so that is what is called permutation. Now, by this question, what I mean is, understanding this means if I give you a gate, okay, let's say I give you whatever reversal gates are, let's say AND gate, okay, swap gate, okay, or the Fretkin gate, or let's say Toffoli gate. So the question is what will be a representation of a permutation matrix can realize this? Now, how do we realize this? So this is a question to answer. Okay, this is a homework. I'll give it also in the assignment, by the way. So the question will be, how do I realize this kind of reversible gates, okay, as permutation matrices? Okay, I'll discuss this again, by the way, when we'll talk about quantum gates, and there will precisely design those matrices. But the way we design the matrices in quantum computing, okay, because in quantum also we'll have C-naught gates. So this is the classical analog of these quantum gates, or you can say those are quantum analog of these classical gates. So there we'll actually find out all those matrices, okay. But there, the fundamental difference between this relation and that relation is, okay, that there we have an advantage, that the bits, the bits are qubits, so they are vectors, okay. So we can apply some idea of basis. So this is kind of a linear transformation. So there will be some basis. So so there will be a matrix multiplication and so on. Okay, so we'll have a new interpretation there. But here my question is, can you realize this as what is called as permutation matrices? Okay. Yeah. So now I think anything else about classical? I don't think so. Let us
How
now
can we
go.
realize and in terms of permutations, sir? Because one, if you are writing 1 plus 1, then that will be like XOR, right?
Think about it. That is the question here. It is
Okay.
possible. The hint is it is possible. Okay. It is possible. There is a way out. Okay. There's a way out. Okay. Now we'll talk about this quantum gates. So let us first. So this is quantum gates. Okay. In fact, you'll see the quantum version of the classical NOT gate. Not exactly classical NOT gate. We'll talk about it. Okay. We'll see that. Okay. So let's say quantum gates. Okay. Okay. So this is, let's say, first of all, 1 qubit. So whenever I say it is 1 qubit, that means, okay, so the gate must be a unitary matrix, which is from C square to C square. So it means U is of dimension 2. Okay, so U is a unitary matrix whose dimension is 2. Okay, and obviously the Pauli matrices, okay, are of course quantum gates. So you can say the identity matrix is a quantum gate. So it does not do anything. It produces the input is same as the output. You can say there's sigma x, which is 0, 1, 1, 0. And you can also have y gate. I mean sigma y, the Pauli matrix, which is 0, I think minus I 0. And I think z or z, which is 1, 0, 0, minus 1. These are of course what is called this one qubit gates, and these are very, very fundamental gates. Why? Because any so any matrix of order 2 by 2, because this will also give you a basis for 2 by 2 vector spaces, vector spaces of matrices of order 2 by 2. So any matrix can be written as linear combination of this 1x y z, and of course then any unitary matrix also can be written as a linear combination of these gates. Okay, so yeah, and not only that, when you talk about physics, I think it must have done, but let me just tell you, I will not discuss what it is, but there are some there is some Hamiltonians, okay, that appears, let's say there are some kind of interaction between qubits, okay, and if this is called something called Ising interaction. Ising interaction, you may just if you have not done this interaction. So here the Hamiltonian here, which realizes this, which is called Ising, okay, is like this Z1, Z2. I'll tell you what are 1 and 2. Okay, then if there is something called the XY kind of interaction. Okay, so interaction, then the Hamiltonian corresponds to, I think it is like this, x1, x2 plus y1, y2, some kind of this. Okay, so there here this 1 and 2, these have some meaning. It means, so suppose you take, so because it is an interaction between two qubits, so there are two qubits, so it is like c square tensor c square to some c square tensor t square. One, when I write 1, this in this parenthesis, so it means, so this j operator like sigma z, okay, here this is acting on the first one. If it is 2, then it is acting on the second one, and so on. So this is on the first one, x1, and x1 means the x operator acting on the first qubit. Okay, times so here, I mean, you can have, let's say, 0, 0. Okay, this is the system. So if you are applying Hamiltonian on that, so then like on the first 0, it will apply here and then here, and then this will also apply on this one and this one. So yeah, this is a parenthesis. So these Hamiltonians are interesting Hamiltonians which appear in practical life. Okay, so I just wanted to make a note of it. Okay, and then the property about x, okay, is very nice. Okay, this x among all this, 1x yz. So this is very, very important. Okay, in some sense, because you see what is happening if you apply sigma x or this x gate, okay, to the computational basis. So what is happening? So let's say it is actually called a NOT gate. So what is that? What is happening? Let's say my x, which is now I'll call it a NOT gate, okay, which is now 0, 1, 1, 0. By the way, this is the permutation matrix, okay. So so the thing is, okay, so this is just a hint, okay. So 1, 0, 0, sorry, 0, 1, 1, 0. These are the columns. And if you just apply this on 0, okay, what do you get? So this is, okay, since we are doing it for the first time, let me just write it down. 1, 0 times 0. So 0 here means 1, 0, okay? So whenever I write, okay, so this is just for notational convenience. Whenever I mean 0, so this is 1, 0. This mathematically, this is the vector. And when I write 1, this is 1, 0. Okay, this is the notation. So don't get confused with 1, 0 and 0 on these vectors. Okay, the first element, okay, in the basis is always 0. Okay, basis means if you consider c square, the space c square, okay, so you have this basis, right? This is spanned by, okay, I'll not, okay, so in math 2 notation, this is spanned by, let's say, okay, well, 1, 0 and 0, 1. Okay, let's say this is my ordered basis. So first entry corresponds to 0 and second entry corresponds to this 1. Okay. Yeah. So don't get confused with this 1 0 and 0 and 1 with 1 0. Okay. Oh, both are 1 0. No, this is 0 1. Okay. So yeah. So if I do that x times 0, so what do I get? I'll get this to be 0 1. So this is 1. And if you do that, so it is 0 1 1 0 times 0 1. Okay, so this will give me, yeah, so 1 0, so which is 0. So what is happening here is, yeah, 0 goes to 1 and 1 goes to 0. So it is just like the classical NOT gate, because for classical NOT gate, 0 goes to 1, 1 goes to 0. Okay, here the same thing. In classical gate, we had bits, now we have qubits. But there is a question, and this question is very, very fundamental. Does it, I mean, is it really, okay, a replica of classical NOT gate? And the answer is no. What I mean by this, I'll discuss it a little more detail, maybe a little later. So what I mean by this, in classical gate, you have only possible 2 bits, which is 0 and 1. But in quantum, qubits need not be of the form 0 and 1. So qubit could be, so I can always have a basis like this. So what I mean by this is an element of C square, and this is an element which is perpendicular to this. Okay, and this is a state, so its norm is 1, and here the norm is 1, but they are orthogonal. So the question will be, does always X take this? So does always X take this to this and this to this? If this is the case, then only I can say this is a true replica of NOT gate, because the difference between classical NOT and quantum NOT, in classical NOT, we only have 2 possibilities, 0 and 1. But here we have infinitely many possibilities. So we can have infinitely many bases, like psi and psi star. Okay, I mean psi part means the perpendicular, which is perpendicular with respect to psi. So here the meaning is psi parp is equal to 0, and both are 1. So they are of unit norm. So this and this. Okay, so then the question will be, is it really a replica of a classical NOT gate? And the answer will be no. Okay, we'll see that little later. Okay. Now there is one more interesting gate, which is actually there is no classical analog of this gate. Okay, and that is which is called NOT gate, as square root of NOT gate. This is my, let's say, second gate. Okay, what is square root of a matrix? Okay, let me just define it this way. Okay, NOT,
Does there
which
exist
is
a true NOT gate?
no.
No. Okay.
So 0 1 1 0 to the power half, which is equal to, let me define it this way. Okay, so half plus I by 2, half minus I by 2. Oh, this is not minus half. Okay, so just half, and then half minus I by 2, and then half plus I by 2. And you can check that this, I mean, square root means if you multiply this 2 times, okay, so I mean, if you multiply this with itself, it should give you the NOT gate. Okay, you can check that. Okay, and another way to check this is like, okay, let us apply square root of NOT gate on this one, half. So if you apply that, okay, what do you get? 0 here means 1 0 vector. Okay, so you can just multiply using just math 2, just a vector matrix multiplication. So it is half minus, so it will just be the first column. Okay, so because, okay, so this is another thing. When you apply this thing, if you have matrix and this, so this will always give you the first column of A, and this will always give you the second column of this. Okay, this is just an observation. You can check this. So where A is equal to, let's say, 1 A2. Okay, you can just check, because these are the first basis element, second basis element. Okay, in the case of qubit, if you have multi-qubit, you have like 0 1 2 up to, let's say, square root 2 to the power n minus 1, like n qubit. Then the same thing, when you take the basis elements, standard basis, the canonical basis, if you multiply, you will keep on getting each of the columns individually. Okay, now again, if we apply this, so again apply, let's say not gate, okay, then you see that it will give you 1. And the same thing is also true when you take this. So let's say not, so you'll get something. Again, you apply square root of not, which is 0. But the question is, so if you have repeated application of this not gate, I mean 2 times, then it will give you the relation of not gates, and that is why. So basically the same thing. So if you take the square of it, then it will give you not gate. But I said this is a gate, 1 qubit gate, which is non-classical. Okay. Do you have any idea why did I say this?
What?
This gate is non-classical in a sense. You cannot imagine this kind of a gate when you do classical computation. It's a purely non-classical gate. I mean, this kind of gate you cannot have in classical computation.
Okay.
So what do I mean by this? This is non-classical. What's the meaning of non-classical? Any idea?
In classical, when you change, you only change from one bit to other bit, but this root not gate has capacity to change from one bit to superposition of 2 bits. This superposition is not possible in classical, right? So yeah, that's why we can't realize this gate in classical scenario.
Anybody else want to say and add anything? I mean, the
The
question.
output
Okay, go
space
ahead.
is bigger than the input space, I think. So, no,
Output space.
not really. No, nothing.
Okay, think about it. Okay, so there will not be any question regarding this. What I meant by this is actually, let me give you a hint. Suppose you want to realize the gate by repeated application of another gate. Do you have this kind of a situation in classical gate or not? That's the question here. I mean, this NOT gate is realized by repeated application of square root of NOT. Can you have a similar situation in classical computation or not? That means, does there exist a gate, classical gate, which can be realized as a repeated application, okay, of another gate? Maybe 2 times application of another gate. Can this happen in classical computation? That is the question. Okay. Now let us get back to our question here. So this is just an example. So is NOT gate clearly a NOT gate? Okay. So this is that really, and in this quantum NOT gate, let's say, is it really a replica of the classical NOT gate? And answer was no. Why is that? Because you just consider any bit, any qubit. Okay. So let us say, let me answer that. So let us say this is just a what is called a general representation, okay, of a qubit which you discussed earlier. So I phi and then sine theta by 2, and then it is 1, right? So this is psi. Then what is psi perp? What is a gate? What is a state which is perpendicular to this? Can you give an example? Can you create one which will be orthogonal to this one? So what I'm trying to tell you is, you choose any qubit. Okay, doesn't matter. You can always create an orth. So if you just look at the picture, although it is not a right picture because
We can just
it is.
exchange them, right?
Yeah, so it is not a right picture because this is real, okay, r square, not c square. So if you pick any vector, doesn't matter, any unit vector, there is always a vector which is orthogonal to this, right? So this is always possible, okay? So that's why this psi doesn't matter. This is also not a right picture, but let us assume that this is c square. So this line is c, the x-axis c, and this also is c. So you have a 2-dimensional plane here, 2-dimensional plane there. So you can always have this, or you can assume it like on the block sphere, okay, you pick one particular point on the surface, okay, that will correspond to a qubit, okay, and then always you have something which is perpendicular. By the way, so since I did not discuss block sphere, just a simple question. What do I know by why how do I imagine 2 orthogonal vectors when I make an angle like this pi by 2? But see, in block sphere that is not happening. Okay, the question will be, okay, because I did not discuss this, So I mean, this is not very, this is very fundamental because you can think about it and maybe you can realize something about the block sphere. What is the North Pole? What is the South Pole?
They are orthogonal. They are like diametrically opposite.
Yeah, but so is it the angle pi by 2? Then what is happening here? That's my question, simple question. So what is the North Pole? Is it the 0? Is it the 1 or which one? Okay, think about it. Okay, you can tell me this answer at least. So which one is 0, which one is 1? The North Pole is 0 or the South Pole is 0?
North is 0
No,
and bottom
no,
is 1.
yes.
Okay, okay, if that is the
Standard.
case, okay, if that is the case, then why is the angle vanished? Why it is not pi by 2? Or in what
How?
sense it is pi by 2? That is my
It's not
question.
like
You don't have to answer this.
representation of, it's not like C square representation. The space is not like C square. It's actually a sphere. So
So, but they are vectors, right? They are vectors embedded in a space. It is in R3, right? This is embedded in R3 because it's a
yes, yes.
three-dimensional picture, right? It is embedded in R3, and we are saying that this is orthogonal. Yeah, they are orthogonal, of course. Okay, the way we write key 0 and 1, they are orthogonal. But when you look at in the sphere, then they are not because they're not. Perhaps they, I mean, apparently it seems like they're not because their angle between these two vectors is not pi by 2. Okay, I mean, if it is pi by 2, then in what sense it is pi by 2? Then that is the right question to ask. Okay, so it's just a question. Okay, for you, you can consider this as just a homework. Okay, just to think about it. Okay, just to think about it just to understand what there is a nice geometry inside this block sphere which you can possibly understand. Okay, so there is nice, but we don't have time to discuss all this. Okay, so now, okay, so we started with a state psi and then we have psi pop. So then my question was, okay, can you give me a state which is orthogonal to this? So this psi. Okay, let me just write one. Okay, I think you can guess it, but still let me just write one. I think this will do the job. So it is like that. Okay, one. Okay, so then you can possibly see that they will be orthogonal. Now we apply the NOT gate on this one, psi. If you apply the NOT gate in psi, that means you have to apply, I mean, you just have to do a vector matrix multiplication with this permutation matrix. So, and this will be the vector representation of the psi is cos theta by 2 e to the power I phi sine theta by 2. Okay. Yeah. And if you do that, you will get this. So e to the power I phi sine theta by 2, and then the other entry is cos theta by 2. Okay, so if you want to write in terms of qubits, you can write it e to the power I phi sine theta by 2, 0 plus cos theta by 2, okay, and 1. Question is it, so multiply, so is it orthogonal to this one? Is it orthogonal to psi? If it is, then you can possibly say, okay, so this X gate realizes it is a replica of classical NOT gate, but you can find out that this is not orthogonal to psi. So Xi, I'll just write it, okay. This is not equal to psi star, psi part. So it actually, it's not a replica of classical NOT gate. It is something which is different from classical NOT gate, okay. So in fact, let me just make a conclusion. There is no universal quantum NOT gate. Okay, so that's the conclusion. Anyway, now let me introduce one more gate, which is one of the fundamental gates in entire quantum computing. Okay, many algorithms can be just developed, I mean, explained using this particular gate, which is very simple and which is called, let's say, I think this is third gate. So this is Hadamard gate. Okay, Hadamard gate, and I'll tell you why it is fundamental also. So this gate we usually denoted by this matrix 1 by root 2, then 1, 1, 1 minus 1. Okay, so what does it do? Okay, this will take 0 to 1 by root 2, 0 plus 1. Sometimes physics people will write it as plus, and H1. Okay, it is just the second column, so which is 1 by root 2, 0 minus 1. So people will, physics people write it as minus, plus, minus. So it takes 0 to plus, okay, and this to minus. And interestingly, if you have n qubits, let's say all are 0. Now I'm giving you a situation where you have n qubits, and on each individual qubit, we are applying Hadamard gate, and then you try to find out what is the output. What is the output state? Okay, so see the power of, I would say, the power of Hadamard. And that's why it is very, very fundamental, Hadamard. So let us take 0 and then apply Hadamard on this. So basically what is happening is, if I just draw a picture, you have this, a register, quantum register, okay? And then if you apply on individual this thing, okay, then there will be a new state, right? So I'm writing at this as a different quantum register, but it is the same quantum register. Okay, yeah. So yeah, this is my question. So what is that? Okay, this is my question. Okay, so when you apply, I would say this is sometimes written as h times n. This times is like a tensor product notation because we're applying. So basically, what you are doing here is, if I precisely write it, so this is kind of like acting individual, acting this h on individual gates. So you are doing this. Okay, 0, 0, 0, 0. Let me write it this way. There are n zeros. Okay, so then if you do this vector matrix multiplication, it is a0 times a0. This is the definition of tensor product times a0. Okay, my question is, what is the output here? Okay, let us see what is the output here. So if we apply this, then it will be 0 plus half. This is the plus 1. Okay, and then you keep on doing this for all these qubits which are at the state 0. And then you have this again. Now, what do we have in the right hand side? What is the output? The output is 1 by root 2, 0 plus 1, again 1 by root 2. Okay, let us write it here, 0 plus 1. Okay, this is a tensor product, by the way. So let me just write here as tensor product like this, and it goes on up to this 1 by root 2 plus 1. Now, who can tell me if I do this tensor product, what do I get? If I do this tensor product, what do I get? In
All
fact,
the basis elements with equal probability.
yes. So this is 2 to the power n. Okay, yeah, you're right. Let us just write j here. So and j is equal to 0 to 2 to the power n minus 1. Okay, because this is an element of c to the power n times c to the power n times c to the power n. So which is approximately, you can say, or isomorphic to c to the power 2 to the power n. So there are 2 to the power n number of basis elements, and those are written the standard basis, the canonical basis. Okay, they are written as this 0, 1. This 0 and that 0 are different. Okay, this 0 corresponds to the first element of the basis of c to the power 2 to the power n. Okay, 2. Okay, so on up to 2 to the power n minus 1. I mean, for example, because we are in the beginning. So if you take just n equal to 2, let's say, so we write the basis as, let's like 0, 0, 0, 1, 1, 0, and 1, 1. This is the basis, the canonical basis of c square times the tensor c square. But this can, again, sometimes we'll write it as 0, 1, 2, 3. Okay, where this 0 corresponds to this one corresponds to this one, and this corresponds to this one, this corresponds to this one. Okay, so yeah, this is why I'm using this notation, this j. Okay, now what is the big deal about it? I mean, why it is so big? This result is so big. The thing is, if you prepare, okay, n qubits independently, n qubits in the state 0, then you are creating a superposition of all possible canonical states of n qubits. So the superposition contains exponentially many terms, meaning 2 to the power n number of elements you have the right hand side. This is exponentially many terms, but you have prepared this with the use of only polynomial number of operations. Only n operations we have used. Okay, so and this is a great deal about quantum algorithms. Okay, I'll repeat this again. So here, this superposition is exponential because you have used 2 to the power n number of operations. Okay, the superposition of 2 to the power n number of basis states. But in order to prepare that, okay, you just need n operations. So you can realize exponential using polynomial number of operations. And this is one of the fundamental thing about quantum. In fact, you will see that most of the algorithms, this is this uniform superposition. Uniform why? Because if you now measure this, okay, so for example, okay, I mean sometimes people get confused with all the notations. So let's say n equal to 2. Okay, so then what will happen is you have h times h. Okay, this is acting on 0, 0. This is what I said actually when for all n. I'm explaining this in terms of n equal to 2. Then what you get here is 1 by 2 to the power n, which is 2, so 1 by 4. In fact, it is half. And then it is 0 plus 1 plus 2 plus 3. Now, otherwise, you can also write this as half 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. But you see, there's 4 elements. This basis element like 0, 0, okay, 0, 1, 1, 0, 1, 1. This is the computational basis of C square tensor C square, because this is the canonical basis of this. Okay, this is the computational basis, the standard basis, computational basis, or you can say sometimes standard basis of this. So you can perform a measurement with respect to this basis. And if you do that, what are the probabilities that you will get all these individuals? You'll get the probability is same. So it is kind of a uniform distribution. You'll get this with probability 1 by 4. You'll get this with probability 1 by 4. You get this with probability 1 by 4. You'll also obtain this with probability 1 by 4 after the measurement with respect to this basis. Okay, so that's why it's a very, very big deal. In fact, you'll see that in most of the quantum computations, so this is this is, I mean, this state, this uniform superposition of all standard states or the canonical states. This is used as an input. Okay, let me just make a remark here, which you will see later. For example, if you want to use search algorithm like Grover search, they will see that this is what is the input. Okay, so remark is that okay, in many quantum algorithms, okay, this state is used as an input, and it is easy to prepare. See, I said if you want to do quantum computation, there are 3 things you have to do. One is prepare. The initial state you have to prepare. So if you state the initial state, I mean, if you prepare the initial state as 0, 0, 0, 0, 0, all are in the 0 state, whatever it means. Okay, by the way, I mean, I did not say this because I think you know in quantum mechanics, 0 here has no special meaning. It's a mathematical representation. Any physical any physical quantity which has 2 degrees of freedom, kind of a thing. Like there are 2 different, there are 2 orthogonal states. Okay, like spin up, down, whatever it is. Okay, whatever it is, like photon, this polarization of these photons. Okay, like horizontal particle. I mean, there are two kind of states which you can distinguish, and they're orthogonal. Okay, so that again always can be written as 0 and 1. Okay, so it is like a unified framework. When I was saying 0 and 1, it's just a representation. Okay, 0 does not always mean 1, 0 and 0, 1 in physical context. Okay, it is something, some vector. Okay, some vector which are orthogonal to each other, and then we are doing this computation. So it doesn't matter. This entire theory Does not depend on 0 and 1. You can start with anything. You can instead, let's say you want to start with plus and minus. You can do that. You can develop the entire theory. Only thing will be that will be a little more complicated because the 0 and 1, they are just the canonical basis. So they are easy to handle. Okay, that's why we are doing this. Okay, so there is nothing special about it. The special thing is only is computation. I mean, all these notations and other things to understand the subject. Okay, but 0 1 can represent anything in physical reality. Okay, so this is one of the fundamental things in quantum computation. Okay, used as an input. And another note I want to make here, and this is a note because this will be used. I mean, I'll use this whenever I'll consider, let's say, Fourier, quantum Fourier transform, something like that. Okay, yeah. So what is this effect of this H? Oops, H. Okay, H0. Now see, what was that? This will go to plus. So 1 by root 2, 0 plus 1. And 1 by this is 1 by root 2, 0 plus, sorry, 0 minus 1. This is minus. Now I can unify this 2, and I can write this entire thing in one equation. Okay, this is h, x could be 0 or 1, and this is 1 by square root of 2, 0 plus minus 1 to the power x, 1. So only change is happening here. This is the relative phase, and that is an observable, by the way, in physics. Okay, so you want to measure this relative phase, so that is an observable in physics. So anyway, so this is a nice thing. I mean, this one equation you can open that, and this is a nice trick. Okay, which this is a nice trick which I'll use. Okay, later on in order to explain, let's say, Grover search, quantum Fourier transform, and so on. Okay, this is very useful. Okay, and now here you see x is just classical, 0 or 1, doesn't matter. Okay, either is 0 or it is 1. So this Hadamard gate is particularly very interesting. And now I'll talk to you about something which is another something which is fundamental in terms of physics. Okay. So the another gate is what is called a phase shift gate. And so the significance of this will be understood a little later when you will see the effect of this gate. And this is, I'll denote it as this, but don't ask me why I'm denoting as this, because you'll realize in a little while. There's a parameter delta, which is, let's say, real. And I'm defining this gate as this unitary matrix 0, 0, e to the power I delta. This is E, yeah, e to the power I delta. Of course, this is a unitary matrix, okay? But what happens to this? If we apply this on 0, I'll get 0. And if I apply this on 1, I'll get e to the power I delta 1. Now, since this global phase, okay, here, okay, is not, it doesn't have, let's say, physical meaning. So I can always say 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. So the computational basis goes to computational basis. But there is a catch. And the catch is, if you apply this, okay, the meaning of this, okay, will be clear when you apply this on a generic representation of a qubit. So if you apply this on, let's say, 0 to the power I delta, and then psi. Okay, the psi is a generic qubit, which is cos theta by 2 to the power I phi sine theta by 2, and then to make a product, then what is happening here? So then this will be cos theta by 2 e to the power I phi plus delta, okay, sine theta by 2. Then what is this? This is nothing but cos theta by 2, 0, plus e to the power I phi plus delta sine theta by 2. So what was the original psi? Original psi was this. Psi is cos theta by 2, 0, plus e to the power I phi sine theta by 2, 1. And see the change here. There is a change. That's why it's called phase. So it is again changing this. It is changing the relative phase. Okay. Physically, this has a huge meaning. Why? Because physically meaning in the block sphere, geometrically, let's say, not physically, but let's say geometrically. This when I write this, a generic state, a generic qubit in terms of theta and phi, this theta and phi, there are some angles in the block sphere. Okay, so if I draw it, okay, so if I take any qubit here, let's say, oh, I should have taken it. Anyway, it doesn't matter. So then there is an angle here, and there is one more angle here, let's say. Okay, so yeah, so maybe here. Okay, anyway, so I'm not good at drawing. So yeah, so you know this, right? So you have done quantum mechanics. So there is a significance of phi and there is a significance of theta. And why does phi, here the phi is only changing? This phi is changed to phi plus delta. So you are perturbing phi only and everything remains fixed. So you are changing that angle, okay, with that angle with this one. Okay, so you are only changing this part. So you are changing the phi. What does phi represent in this block sphere?
It'll be the angle.
Don't consider this picture. This is misleading. Huh? Okay, what is that?
When you project on xy plane, angle made with x-axis is phi.
Anything else? Anybody else? Guys, you will little bit read block sphere. Okay, so because I did not discuss this, so okay, let me make the conclusion here, and you can go back and see. Okay, the effect of this gate is actually okay a counterclockwise rotation through an angle delta about the z-axis or the z-axis. Okay, think about that. Okay, that this is nothing but it will give you a phase shift. Okay, if in geometry it is actually this what is called anti-clockwise. Counterclockwise rotation or anti-clockwise rotation. Okay, around this z-axis. Okay. So not only that, this gate has another very interesting property. Suppose, so here an application of, that's why I wrote RZ. R stands for rotation, Z for around the Z axis, and delta is by an amount delta. Okay, so that's why RZ delta. This and Hadamard. Now the question is, suppose I want to create, okay, a state psi, which is cos theta by 2, 0, plus e to the power I phi sine theta by 2. Now I'm giving you a recipe how to do that. I'm saying, so this is one of the, say, I will always refer to our my previous discussion. Quantum computing means first need to prepare, okay? First you need to prepare the state, okay? The question is, I want to create a state. How do I create it? Any state, qubit is nothing but this. So then the question is, for any specific value of theta phi, how do I create such a state, okay? Using quantum gates, let's say. And here is the answer. Answer is, I can always create this state for any value of theta and phi from 0. If my initial state is 0, and I take the gate as the following. RZ phi by 2 plus phi Hadamard times RZ theta and then H. Basically, it is matrix multiplication, but it's a repeated application of this gate. So what I'm trying to tell you is, you have this 0 here. This is the input. First apply H, then apply here, let's say RZ theta. Again apply H, and again apply RZ pi by 2 plus phi. Okay, and then you'll see the output is actually psi. So theoretically speaking, this can always be created. Any state, any qubit state is always possible to create. Okay, you can always create any qubit. That is not a problem. But there is a catch, and the catch is this is in theory. And why in experiment this could be a challenging thing? Because you need to realize these gates using some physical experimental apparatus. Okay, so first of all, you need to create this state 0. Okay, this state, the input. And second thing is you need to realize all these operations. So again, you see, I said in quantum computation there are three things. One is preparation. Second thing is realization of unitary operation, and third thing was measurement. Okay, so here is how do we create such a thing experimentally? How do I realize this gets these unitary matrices? Okay, experimentally, that could be a challenging thing. That could be a challenging part. Okay, but this is homework. Okay, you can just multiply it and check whether this is true or not. So if this is true, then any states, qubits, okay, in this world can be created. Doesn't matter. Now, since this RJ, see, RJ, I said it's a phase shift gate, okay, and I define directly this, and then I observe that it is rotating the qubit, okay, around the z axis by an amount delta. Then my question will be, okay, can I have a gate which will rotate my qubit on the sphere around x-axis, around y-axis, or around any arbitrary axis? Answer is also true. Yes. So then I have to dig on this. Okay, what is this? How did somebody get it? Okay, so what is the meaning? How this can be derived? Like how can you reach to this? What is the connection of this gate, okay, with other gates which I already defined? So if you want to do that, so I'll discuss first this thing. Okay, this is just what I'll say the preliminaries. Okay, before I do that. Okay, now consider any matrix. Okay, consider any matrix M. Okay, such that M square equal to identity. Any matrix M square. If you take the square of it, it is identity. Just like NOT gate. Is it? NOT gate, does it satisfy this? Okay, let me check. M is equal to 0, 1, 1, 0, and take M square, which is 0, 1, 1, 0. Let us multiply and check what is happening. 0, 1, then 0, 1, it is 1. 0, 1 goes to 1, 0, it is 0. 1, 0, 0, 1, 0, 1, 0. Oh, this is 1, identity. Okay, so M square is identity. And if M square is identity, if you take any power of M, let's say M to the power K, then this will be identity if K is even. You can always find out this. And it is M if K is odd. Okay, then what is happening? If you have such a matrix, then e to the power, let's say minus I, okay, some parameter, let's say, yeah, whatever, let's say theta. Okay, I mean, I don't want to make things, okay, let me write delta because the delta was the change. So delta, okay, no, not delta, but let me, because I'll use this data a little later. So maybe it is alpha, okay. So some alpha, and then M if you want to compute what is happening. So this is exponential of a matrix. You can use the formula, okay. And then if you use this result, because this M satisfies M square equal to identity, and M to the power K, then you will see that it is nothing but this. You just write down the exponential formula, like your e to the power x, the Taylor's expansion e to the power x, just replace x by minus I alpha M matrix, okay. So just do that and just find out that this will be nothing but 1 minus 1 by root 2 alpha square dot 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 times I minus I because of this property. Okay. I alpha, okay, alpha minus 1 by factorial 3 alpha q dot times m, and this will be always cos alpha times identity minus I sin alpha times m. Now, why did I talk about this m? Because this is a property of any Pauli matrix. So this X matrix is not a special thing. It's not accidental. This is a property of any Pauli matrix like sigma X, sigma Y, sigma Z, and of course identity. Okay. So that means for those matrices, Pauli matrices, this formula is also valid. Okay. Now, this is the preliminary. Now, if I compute e to the power minus I delta by 2 and sigma Z, so then what do I get? This is cos delta by 2 identity because of this formula I sine delta by 2 sigma Z. And if you just write I and sigma Z, then what do you get? This e to the power minus I delta by 2 100 e to the power I delta, which is actually, you can say, RZ delta. Because if you apply this gate, so this will be just a global phase which has no physical meaning. So if you apply this on a state, on a qubit, then only this will get multiplied, let's say. The entire thing will get multiplied, but this has no meaning. So this can be, this RZ delta has same effect as this one. So RZ delta, RZ delta, okay? This rotation about Z, the axis Z, is nothing but this matrix. So once I have this, then I will say, okay, then let us multiply also, I mean, let us do the same thing also for sigma X and sigma Y and see the difference. And I can do that. Minus I delta by 2 sigma X I can take, and you will see that they give the same effect on the qubit. That means they will rotate the qubit psi on which you are applying. Okay, they'll rotate the qubit. Okay, her qubit is the vector on the surface of the Bloch sphere. Okay, and okay, let me just write down this matrices, and then you will see that, yeah, so they do the same thing. So this is cos delta by 2 minus I sine delta by 2 minus I sine delta by 2. This is cos delta by 2. And here, so, okay, let me write it also as this R x delta. See here, when I'm writing delta, here this guy is delta by 2. Okay. So, and this is what is called Ry delta. Okay, which will be cos delta by 2 minus sine delta by 2, sine delta by 2, cos delta by 2. Okay. Now the thing is, these are very, very special qubit gates, right? Because they are obtained from the from the Pauli matrices, right? Now my bigger question is, okay, they are very special, and why I'm talking about this? Remember, just remember that when I talked about evolution, quantum evolution, we had this Hamiltonian matrix. Okay, so the Schrodinger equation. Okay, and then we said, corresponding to this Hamiltonian matrix, what is the corresponding unitary operator? This was something e to the power minus I think h hat h, something like that. Okay, so the Hamiltonian is independent of time here, constant. Now Hamiltonian matrix, I said that this is, I'll always consider this as a Hermitian matrix. And this is a 2 by 2 matrix. Let us assume for the time being that we are talking about evolution, dynamics of a qubit, which is a 2-dimensional system. And this is a Hermitian matrix of order 2 by 2. So this matrix can always be written as a linear sum of Pauli matrices, because Pauli matrices gives you a basis, okay, for the 2 by 2 matrices. And this is a 2 by 2 Hermitian matrix. In fact, Pauli matrices have more properties. Pauli matrices are such matrices which are both Hermitian and orthogonal. This is very, very rare. I mean, if you just look at this this Pauli matrices, all of them are Hermitian and all of them are orthogonal, I mean unitary. Okay, I don't know, where did I write it? Okay, so yeah, here. You see, they are all Hermitian and they are all unitary. So then the question is, if I write this H as the linear sum of this, and then if I take e to the power something like this, so then it will be e to the power some constant, whatever it is, okay? And H as sum of this sigma x, okay, or sigma s, where s is equal to, let's say, 1, 2, 3, 4, the Hermitian, that's the sigma s. Then I want to realize any unitary matrix. So then the question will be, do these matrices which rotate this Rx, Ry, and Rz, do they have any role to implement to express any unitary matrix which can be written as this? Okay, this matrices, this rotation matrices, do they have any role? Okay, in order to implement U. So I want to implement any unitary matrix in this world which is of order 2 by 2. And I want to do that using this rotation matrices. And why do I think about it? Because I know this is, they are playing a role here. Okay, the same thing is here. This is exponential to the power something. Okay, where sigma 1 plus sigma 2, some combination of this, scalar combination of this. Is it possible? And the answer is yes, it is possible. Any unitary matrix of order 2 by 2, that means any one qubit gate, okay, can be realized by this rotation matrices and one more matrix, which is called the phase gate. So the phase gate is this. I'll introduce one more, this gate, which is, let's say, delta here, to the power I delta and 1 0 0 1. This is this identity matrix to the power I delta. Okay, it's very simple gate. So it is not doing anything basically, because in order to change the phases, sometimes I need this. So then the question will be, how do I do that? How do I decompose this unitary matrix in terms of some well-known gates, some gates or some other unitary matrices which are fundamental? And the answer is, this is always possible. Okay, you can check that. You consider any unitary matrix U. This is any one qubit gate, and you can always write this as RZ something. Let's say some. Let's say, what do I write? Let's say RYB. This is product, and RZC for some ABCD, and then phase gate D. For some ABCD, it is always possible. How do you decide the value of ABCD? Maybe I'll talk about it next day, but this is always possible. In fact, yeah, this is always possible. In fact, all this, if this is the case, if this is possible, then all the well-known gates, which I already discussed before, they should also be represented as this for some value of ABCD. Okay, and I give you some examples. Okay, first example, NOT gate. NOT gate can be represented at this, Rx pi times this phase gate 5 by 2. Then NOT gate again can also be written as this, Ry pi Rz pi pH pi by 2. Okay, the square root of NOT gate. Okay, let me write only one representation because otherwise it will take a lot of time. Pi by 2, pi by 4. And there are multiple ways to do that. So let me give you just one. Okay, and the Hadamard gate also can be implemented as that. I mean, any gate, so any unitary matrix, why not this? So it like you can say Rx pi times Ry pi by 2 and pH pi by 2. Okay, sometimes I do a lot of mistakes writing that things down. So this is a homework to check. This will be a nice thing to check, and maybe we'll discuss this. Maybe we can spend 5 minutes about that. So yeah, any unitary matrix can be written
Check what,
as
sir?
this.
Check the examples or the or
Examples, of course, but also this any unitary matrix. How do I write any unitary matrix? How do I parameterize this? This is kind of a parametric representation of all 2 by 2 unitary matrices.
Okay.
Do you? Yeah. So the question is, do you know any matrix? I mean, do you know any parameterization of all unitary matrices? That's the question. Okay. If that is the case, I mean, parameterization means this matrix means you can write some entries here. This entries depends on some parameters. Okay. And any unitary matrix can be realized from this expression, this matrix, just putting some particular values of those parameters. So this is a parametric, and this is given by this actually. If we just multiply for some ABCD, just multiply this and then check whether this is a parametric parametrization or parametric representation of unitary matrices of order 2 by 2. By the way, this is order 2 by 2 only. Okay? So all 1 qubit gets. So I thought of discussing all possible gates by today. I mean, 1 qubit gates at least. I think I have done that. So yeah, maybe next day we'll start talking about 2 qubits gates. Okay, next week there is what is that? I was writing parametric representation of unitary matrices of order 2 by 2. Okay, I think next day we'll start talking about some more gates, which are, let's say, the quantum version of control NOT gate, Fretkin gate, Twelfth gate. Okay, I mean Toffoli gate, and what else? Yeah, and then possibly we'll talk about.
Sir,
Let me see. Yeah, what I'll talk about.
I did not get that bit about iming interaction, sir. Can you just repeat that?
No, this is very, very fundamental. And this is kind of an interaction between 2 qubits, let's say. So just there are a lot of videos in YouTube available. Just go through that. And just click on one of them or just click on Google. So it is available. This is very, very fundamental. Okay, they do it. Okay, or you can ask them in quantum mechanics class. I don't know much about that.
Oh,
So you may
so what
just
did you
ask them.
say about iming interactions? Just that part, can you like repeat?
What?
What
What
did
is
you
that?
say about iming's interaction? You told something about it, right? So that part I
Yeah.
didn't.
So what I'm saying is, so there are suppose there are states. Okay, so these are quantum particles, let's say. So there will be always some kind of interaction between this. Otherwise, this quantum entanglement phenomenon will not occur, right? And the dynamics of see, if you talk about one state and if you talk about 2 states, what is the difference? The difference is in state space, right? So
Hmm.
the dynamics of this is different from dynamics of this. And how the dynamics is explained? Dynamics is explained in terms of Hamiltonian only, right? Using the Schrodinger equation. Then the question will be, what is that Hamiltonian? Okay, for which you get a dynamics of this kind of a state. Now Hamiltonian, you can take any Hermitian matrix, right? But for physics, I mean, there are some interactions, okay, for which can be realized by using this Pauli matrices. Okay, this is what happens for some kind of particles like electron and so on. Okay, so for those interactions can be captured by this kind of Hamiltonians. Okay, so that's why I said those kind of interactions they have name. But this is very, very old thing. I mean, this in physics, this is very, very old, the Ising interaction. So this is very, very standard. By old, I mean this is very, very standard. So yeah, so this is not a big deal.
Okay.
Okay. Okay, if you have any other question, please ask. Yeah.